Have you ever wondered what truly separates a military aircraft from a commercial one? Not in terms of speed or weapons, but in the very structure that keeps the airplane together? Hidden beneath the aerodynamic surfaces of every fighter jet or military transport is a structural design that must survive extreme forces far beyond anything seen in civilian aviation. Understanding these structures explains why military aircraft handle the way they do and why their shapes, materials, and internal components are so specialized.
Here's what makes the structural demands of military aircraft far more extreme than those of any civilian airframe. Military aircraft must satisfy the same basic goals as any airframe: resisting applied loads, maintaining aerodynamic shape, protecting systems, and supporting all onboard equipment. But in military applications, the demands placed on the structure are much more intense. These aircraft have to stay as light as possible to remain highly maneuverable, yet strong enough to handle sudden, violent, and repeated changes in force. They carry heavy weapons, powerful engines, fuel, and advanced electronics. And unlike civilian planes, they often need to keep flying even after taking some damage. Because of this, their structures are built with special attention to strength, fatigue, resistance, damage tolerance, stiffness, and the ability to survive crashes.
A military aircraft is subjected to a wide variety of loads that often occur at extreme magnitudes. During combat flight, the aircraft may perform high G maneuvers, such as tight turns, abrupt rolls, and rapid pitch changes. These maneuvers impose large bending forces on the wings and fuselage, as well as significant torsional loads when the aircraft rolls asymmetrically. Military missions also involve conditions with strong gusts, buffeting, vibration, and dynamic pressure changes, especially at low-level flight or near transonic and supersonic speeds. Shock waves, high skim friction, and rapid changes in aerodynamic forces all contribute to demanding structural loads. Even the ground phase can be extreme. Carrier-based aircraft experience catapult launches and arrested landings, which impose huge loads to the landing gear and the lower fuselage. Military transports operating from rough or unprepared surfaces encounter strong impact loads and require reinforced undercarriage structures. Weapons create their own category of structural challenges. Hardpoints on wings and fuselages must support concentrated loads from missiles, bombs, and various bullets. When a weapon is released, a sudden change in mass and aerodynamics can create abrupt torsional and bending loads. Aircraft with internal weapon bays must be reinforced around these large cutouts so that the fuselage retains its strength even with significant openings. Finally, modern military jet engines generate high thrust and high temperatures. The engine mounts must resist axial loads, thermal effects, and gyroscopic forces caused by the high-speed rotation of compressors and turbines.
One of the most critical parts of a military aircraft is its wing, which is one of the most heavily loaded components of a military aircraft. To withstand extreme aerodynamic and maneuver loads, most wings are built around a strong torsion box made up of spars, ribs, and skin. Different aircraft use different spar configurations: parallel spars, converging spars, or swept arrangements, depending on wing geometry. Military aircraft often have swept or low aspect ratio wings, which are especially prone to twisting at high speeds, so torsional stiffness becomes essential. The wing skin itself carries a significant portion of the structural loads, including shear and torsion. Because military aircraft must minimize weight while maximizing strength, they often use integrally stiffened panels or advanced composite skins. These provide high strength without relying on large numbers of riveted joints. Control surfaces, ailerons, elevons, flaps, spoilers require strong hinge support and reinforced ribs. In addition, the wings may carry external fuel, tanks, sensors, or weapons. Each attachment point adds concentrated loads that must be carefully managed, and the structure underneath must be strengthened to handle them.
Modern military aircraft rely on carefully engineered fuselage structures designed to balance strength, weight, and durability. Most modern military aircraft use semi-monocoque fuselage construction, where the skin, stringers, frames, and bulkheads work together to resist loads. This combination creates a lightweight yet strong structure capable of handling wind-bending forces, landing gear loads, internal pressurization, engine thrust, and the stresses introduced by large cutouts for cockpits, avionics space intakes, or weapon compartments. Military fuselages often include significant openings for sensors, landing gear, and weapon bays. Each of these openings interrupts the load path, so the surrounding frames and bulkheads must be reinforced to maintain structural integrity. Damage tolerance is another crucial aspect. Military aircraft are expected to remain controllable even after sustaining minor damage, so redundant load paths and strong skin-stringer combinations are built into the design.
The evolution of military aircraft materials has moved from early wood and fabric structures to today's advanced metal composite hybrids. Current designs rely on Aluminum alloys for skin, frames, and stringers, offering a good balance of weight and strength. Titanium in high temperature or heavily loaded regions, especially around engines and attachment points. Steel for undercarriage and high-strength components, and composites including carbon fiber reinforced plastics for wings, control surfaces, and fuselage panels. Composites are particularly valuable because of their stiffness, low weight, and ability to form smooth aerodynamic shapes. They also reduce radar reflectivity, which is essential in stealth aircraft.
What truly makes military aircraft structures special? They must endure forces far beyond those faced by civilian aircraft, remaining light, strong, and capable of withstanding extreme loads, high speeds, and harsh temperatures. Wings and fuselage are engineered for an optimal balance of strength and weight, using materials selected for both performance and resilience. In the end, a military aircraft structure is a refined blend of engineering and mission-driven design, built to thrive in the most demanding conditions of flight.